We have a graph here of electric field as a function of x, and the scale is set such that this is equal to 20 volts per meter. Remember, that's the units for electric field, so this would be negative 20 volts per meter. We're asked to find the electric potential at x equals 2, so at this point here. And the greatest positive value of the electric potential for points on the x-axis, less than 6 meters. And what value of x is that electric potential? 0. The equation that we're going to be thinking about then to solve this is that, I'll write it up here, that the change in potential is equal to the negative integral from 0 to whatever position x, e dx. So don't be too worried about that. All that is saying is that the final potential minus the initial potential is equal to the area under the curve, basically, of the e versus dx curve. So if we want to find it from 0 to 2, then all we need to do is find the area under the curve here. Okay, so that's just what we've been doing all along with our integrals. Is we're basically finding the integral of easy to find things. Okay, so note the negative sign. Now this is important. So that's pretty important in this problem. So if we want to find then the the potential, so the electric potential at 2 meters, we're trying to find Vf. Now we're told at the origin, so initially it's 10 volts. So we can rewrite our thing here saying Vf minus 10 equals basically the negative area under that curve between 0 and x equals 2. So we're trying to find the area of that rectangle there. So that's going to be equal to, so Vf equals 10 plus half, well the base times, it's just base times height of this thing, so half 2 times the height, which is 20. So I've taken into account there's a minus sign here, and and this is going to be height of negative 20, so we get a plus at the front there. So we get 30 volts is the answer for A. So the electrical potential, we started off at a potential here of 10 volts, and we end up at this point at 30 volts. So moving through some electric field, you can see there's a potential difference of those of 20 volts between those, but our final potential will be 30 volts. So, and it's positive because of this negative sign here. So we need to be careful about that. So the next question is asking us, so what is the greatest positive value of the electric potential for points on the axis, on that axis, so between 0 and 6 meters? Well, so if we're looking at this region we just looked at, we can see the potential is increasing, and it's always going to be increasing up to this point here, so x equals 3. So let's write that. It's increasing until x equals 3. So after that, we're going to be getting, if we find the area under this guy here, we're going to get a positive value, but because of the negative sign here, we're going to start decreasing the potential after x equals 3. So we're going to build up to some point here, and then we're going to start decreasing. So we need to find the potential at x equals 3. So we can do that very easily. We can just say that the potential equals V max at x equals 3. So then we can just use our equation, V max minus V initial equals negative integral e dx. So basically, again, we're trying to find an area, but now we're trying to find this area. So the area under the curve between 0 and 3 meters. So we can do that, find that area under there. We can say then V max equals VI, and it's negative, but then we find the area is going to be positive under there. So we get, so that's going to become a positive here, plus 1/2. 3 is the base times the height, which is 20. And VI was 10, remember. So we just end up with 40 volts. Okay, so at this point here, we have 40 volts. That makes sense because it's linearly increasing. So we could say that at this point it's 20, 30, and then 40 at this point here. So that's what happens with our potential. It's a linear relationship between the electric field and the position in the electric field. Okay, so for C, we need to find, we know the area here under this guy, that was 40 volts. And we need to find now an area over here such that it cancels out the 40 volts over here. See, they're opposite. This will be the voltage here will be the opposite of the voltage here. So we want to find some position X where you have some capital X, if you like, here, big X, a position where we have got enough voltage, enough potential difference to cancel out the potential difference up to X equals 3. So we're looking for some X greater than, so some big X, which is greater than 3, such that the area from, from X equals 3 meters, so this point, up to this point, the area under that is 40 volts. So, and we're going to some, great X, where X is, X, value X is equal to X. And we need to find that area, this area here, to be that area equals 40 volts. So we can use the formula for a triangle for the area from, from in this range, where X is greater than 3 but less than 4. Okay, so that's this triangle here. So we can use an area of a triangle in this region, so we can say, that's half base times height, which is 1, times the height, which is 20. Okay, that's going to give our area in that region. And then we need to find this other region. It's going to be some sort of a rectangle up to some position X. When X is greater than 4, let's move that around. When X is greater than 4, but less than this capital X, which is what we're looking for, then we're looking for this area of this rectangle here. And the area of that rectangle is just going to be X minus 4, okay, that gives us the length of this bit here, times the height, which is 20, and that's going to give us the area of that. So the addition of both of those guys, those two areas, has to be 40 volts. So then we can set up the equation that says half 1 times 20 plus X minus 4 times 20 equals 40 volts. We're looking for the addition of those two areas to be equal to 40 volts to cancel out our initial 40 volts. If we solve for X here, if we do some things, we're going to get 10 plus 20X minus 80 equals 40. And we can solve for X there, and we get X is equal to 5.5 meters. Okay, so that's, around about here somewhere. So we have 4 charges here, and they are varying distances away from this point P right here. And we're asked to find what's the potential at that point, the electrical potential. Remember, electrical potential, I'll write it here, electrical potential V is a scalar. That means we just find the field from each of those, the magnitude of the field from each of those charges, the potential from each of those charges, add them up as just as a scalar. They're not vectors, we just need to find out what the absolute value of the potential is at that given P, and we just add them up as numbers. So let's go ahead and label our charges. I'll call this 1, whoa, let's not move everything again. I'll call this charge 1, this one's charge 2, 3, and 4. So we'll say Q1 is at a distance, R1 equals 2 times D. We've got Q2's at a distance R2, which is just D. Q3, R3 is also at D, and Q4 is at the distance 4, which is also D. So they're all D away from that point, except for this charge 1, which is 2D away. So it's going to have a smaller contribution to the net potential at that point. So we can then say, well, we know that let's write it up here, the potential is equal to KQ over R. See, that's no vectors, that's a scalar. So if we want to find the potential from all of those guys, we just say V is equal to KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3 plus KQ4 over R4. Okay, we're just adding them up as a scalar. We work out the individual potentials from each one of those. They all add up at that point V. We can make that look a bit neater. We can say that's equal to, let's take our KQs out the front because the Qs are the same. You can see they're all, the size of them is the same, it's just the size that changes. The Q is just 5 femtocoulombs. So we can do that, and then we can rewrite this. Let's put our values for the R's that we have over here. Let's put those into the equation, and we get -1 on 2D for Q1, -1 on D for Q2, +1 on D, +1 on D. If we do some algebra on that guy, we get KQ on 2D. It's the total potential. I better put a T here for total. Put some numbers in. 8.99 by 10 to the 9. We're getting pretty used to using that constant now. Q, we're told, is 5 femtocoulombs, so 5 by 10 to the -15 is femto. Divided by 2 times the distance, which was 4 by 10 to the -2, 4 centimeters. That gives us an answer of 5.62 by 10 to the -4 volts. What we have here is a battery with a switch and a capacitor. Very, very simple circuit. As soon as we start, we close that switch, we're going to start charging the capacitor. We're going to start building up some charge on the capacitor. And that charge will flow until the potential difference across the capacitor is the same as the potential difference across the battery. So when you've got some voltage here, well, we'll keep charging until those voltages are equal. So the charge on the capacitor at that point then is Q equals CV, where C is the capacitance. So that's the same as the total charge that's passed through the battery. So we are asked in this question, how much charge passes through it? Well, we can work it out just using this if we know the capacitance, which is 25 microfarads, 10 to the -6, multiplied by the voltage difference. Okay, so this capacitor has to build up the same amount of potential difference. So it builds charge on the plates on this guy until it's at the same potential difference as the battery. This is why we can use it to store electrical energy in the electric field inside the capacitor. So that gives us 3 by 10 to the -3 coulombs. That's a large amount of charge. In this circuit we have a battery and it's going to charge up two capacitors. Now they are in parallel. You can see this one, C1, has some dielectric inside it. This one has just air in it. So C2 is just, so this has some relative permittivity. And this has got E0 in here. So it's a, air, let's say that's basically just like a vacuum. So E0. It's not exactly, but very close to it. So you can see that I've used the symbol up here, epsilon R. The textbook might use kappa, but it's just the same thing. It's just this, it's a relative amount of, to do with the material, the dielectric material. If a high value of that ER means that this capacitor has a great ability to store electrical energy, it actually increases the capacitance of that capacitor by mucking around with the electric field inside there. Remember from the lectures that the dipoles can enhance the field in such a way that the capacitance is increased. So we put dielectric materials in to do that. So each capacitor has 12 volts across it. This guy here is 12 volts. So that means that each one of these capacitors has a voltage of 12 volts across it once it's charged. So we need to find the capacitance of these. We don't have that. We have a couple of things. We've got the relative permittivity, which is 3. We have the area, cross-sectional area of the plate, 5 by 10 to the minus 3. And we've got the plate separation D, which is 2 by 10 to the minus 3. So we can go ahead and find the capacitance from that because we know, let's see, look at C1. That is, because it has some dielectric inside there, we have to use this epsilon R times epsilon naught times the area over the distance between the plates. So we have 3 times epsilon naught, which is a constant value of 8.85 by 10 to the minus 12. The area, we're told, 5 by 10 to the minus 3. And then we divide through by the distance between the plates, 2 by 10 to the minus 3. And we get an answer there for the capacitance, which is 6.64 by 10 to the minus 11 farads. Small value. Okay, we can go ahead and do C2. We can assume that the relative permittivity of the air, well, let's just call it 1. It's pretty close to 1, so we can just say epsilon naught times A on D, which is 8.85 by 10 to the minus 12 times 5 by 10 to the minus 3 divided by 2 by 10 to the minus 3. And I get a capacitance which is 2.21 by 10 to the minus 11 farads. That's about a third of the other one, and that's to be expected since the relative permittivity is 3. So once we have our capacitances, we can work out what the charge is. That's what we're asked for. How much charge is stored in the parallel plate capacitors. So Q1 is just going to be C1V. Okay, so that's going to be that. When we do that multiplication, we get 8 by 10 to the minus 10 coulombs. Q2 is going to be C2V, and that comes out to be 2.66 by 10 to the minus 10 coulombs. Okay, so this shows you that the dielectric allows us to store more charge. We can have a greater capacitance and store more charge. We have a conducting sphere. It's isolated, 10 centimeter radius. One wire carries a current, there's almost 1 but not quite exactly 1 amp into the sphere. Another wire carries it out. So we've got some current flowing in but slightly less flowing out. How long will it take for the sphere to increase its potential? by 1,000 volts. So we change the potential by 1,000 volts. So we're adding some charge to this sphere, and it's slowly building up because we have a mismatch between the current flowing in and the current flowing out. Well, we can use our potential equation. Let's say the charge on the sphere increases by this small amount, delta Q in delta T, in some time delta T. Then the potential is going to change by delta Q over 4 pi epsilon naught R. This is just V equals Q over 4 pi epsilon naught R, which is KQ on R. Incidentally, this R, if we look at our sphere like this, we want to find a potential, relative to some point. So in the center here, the potential is going to be 0. Okay, because the charge, distributed on this sphere is going to add up to 0. The potential at this point, and then we've got some potential at the surface. So we're looking at this change. So we're looking at over the distance from the center to the surface R. We've got a potential difference, and we're building that up by building charge on the sphere. So that's where the R comes into it. So yeah, we can just write this then as K delta Q over R. So we can rearrange that to get the delta Q out like this. Delta Q equals delta V R over K. Right, we also know that delta Q, so the change in charge is equal to the current in minus the current out. So the net flow of current, delta T. Remember the current, current is just delta Q over delta T. Okay, it's the net flow of charge. So we can say this. We make those things equal. So if we make I in minus I out, these are things that we have. Delta T equals delta V R over K. And we can solve for delta T. So we get delta T is equal to delta V R over K I in minus I out. So therefore delta T, which is what we're looking for, how long does this take to charge up to this potential? Well, we have delta V on top, so 1,000. We have R, which is 0.1 meters. And on the bottom, we have K, 8.99 by 10 to the 9. And then we have the difference, 1.00002 minus 1, basically. Punch that into our calculator and we get 5.6 by 10 to the minus 3 seconds. Pretty fast, 5.6 milliseconds to reach 1,000 volts. And that's only a very small current flowing in and out of this thing, so impressive.